Okay, while we're waiting for some more people to log on, we were just talking a second ago about the videos for analysis of variance. I actually made those up a while ago. Let me show them to you. Made them a while ago for a project that I was playing around with, where I was trying to create a chapter for presumably a statistics book. And iBooks is a specific kind of ebook, electronic book. But it'll only work on Apple platform. At the time I was doing it about 4 or 5 years ago, it would only run on the iPad, so it wasn't very useful. But at that time, you didn't have a lot of the facility that you have in other e-texts that would run on Windows or other platforms that you had there. They gave you a lot of flexibility to embed videos in the textbook and do all sorts of other things. I'll show you how it works. So most of those videos are from there. If you have an iPad, I put a link on Blackboard where you can actually download this and play it on an iPad. It's a big download. I think it's 130 megabytes. But if you're interested, you could give it a try. Okay. Now I had it for the most recent version. Yeah, that looks like the latest version that I did. Been a while since I played with it. Okay, so this is how it would open. It would open up with actually a video, right? If the first time you open it on the iPad, it'll play a little video for a moment or two, and then it opens up to this page, and then it goes from there. It's kind of got some text on how you calculate analysis of variance, some background. It goes through this little slide here. It shows you the assumptions. You can actually play, click down here, play through them. Go to the next page. It continues the information on it. The next page, you have a table, and in fact, these pictures. I don't know if it'll do it here, but if you're in the book, if you use an iPad or another device like it, you can actually click on that, and it'll open up in their own window. And the videos are actually embedded in it, so you can actually, that first video that you saw where I do the calculation, that would actually play here. I'm going to turn the sound up momentarily. You might get an echo if you're online. 5 values, and the last group has 5 values. You can use the analysis of variance to determine
I can hear it. You guys can hear
populations that these samples were taken from.
That's the video that's online that shows you how to go through the calculation for analysis of variance by hand. Now, I'm not expecting anybody who's going to do that is going to go to the trouble of doing analysis of variance by hand. You're probably going to use SPSS to do it. On the last exam, if it comes up at all on the last exam, really, we're just after this. We're after the second exam. We didn't cover it on the second exam. So analysis of variance and linear regression probably be the only problems on the last exam. So if it comes up on there, I'll either give you the option of maybe working with a table produced by SPSS, or I'll figure out some way that if you have a problem. So a lot of students are still having problems accessing virtual desktop. So yes, it is lots of more text and so on and so forth. Here's a second video where it shows how to do the analysis using SPSS. And these videos are on Blackboard, but you can also, if you wanted to. And it's got kind of a neat little feature where you can annotate a table. Like this is the output from an SPSS file. So you can actually, for instance, click on here and it'll expand on what it's pointing to. I'll pick on here, numerator, it'll expand on that. Or go down here, degrees of freedom, and it might tell you how it's calculated for that particular item and the significance and what the meaning of the significance is. So it's kind of like a little bit more than you would get in a regular textbook. And this is a video showing how you run the Post-Hoc Tests. We'll talk about that in a second. Some output again, some more things you could click on for the Post-Hoc Tests that'll explain to you what it means. And then, maybe an exercise. I think a couple of exercises, and then finally a little quiz. So you can actually, answer this little quiz. What are your assumptions? Normal, have the same standard distribution. Independent, have the same standard deviation. The samples are independent and normal. Samples are independent and normal have the same mean. That's not true.
Let's stick with that. Let me clear that. Okay, click that. Let's go to the next question. I'm just going to answer these randomly. Sum of squares between three groups, three sample groups, each contain 10 values. Sum of squares between the three groups is 20. The sum of squares within the groups is 54. So what's the value of f? That must be based on some other question as well. I'm just going to click anything here just to get through it. Go to the next question and drag the labels to the correct location. See, it's kind of cool, right? You have sum of squares over the degrees of freedom. See, so here, sum of squares over the degrees of freedom is here. Mean squares between over the mean squares within. Okay, and that's going to be the F score, which is going to be right here. And finally, the probability value, the significance, is going to be there. So that should be right. And again, you can ask you some other questions, and eventually you can check the answer. It'll tell you how many. We didn't answer the last question. You can start over if you want to. So it's kind of a neat way to present this information. You know, there again, I guess I'm not sure what I'm looking at here. Why this is? Oh yeah, and it actually has also the entire PowerPoint associated with the class on this. Sure. Yeah, there you go. If you click on it, whoops, wrong way. If you click on it, it advances through the PowerPoint. So if you guys want to play around with it, you can download it. All of the real information is already on Blackboard in the weekly session. Who knows? One of these days, now that they're doing so many online classes, it may be worth going back to this and maybe trying to develop something, maybe with a different medium. I know Adobe InDesign will produce ebooks for many different platforms, and perhaps it'll work with. Perhaps they've advanced it enough that it'll give some more of this, the kind of functionality that only used to be on these iBooks. Okay, so let me move on from there. It's interesting, not valuable, but interesting. Okay, don't need this. So let me start by asking you guys, if I'm sure you have some questions. We have the exam 2 that's in progress. I'm sure you may have some questions about stuff that's on there. I can answer general questions, not specific questions. By the way, for you guys in the room, of course, I'm repeating this because we have people online that didn't hear me before. Okay, so you got questions. What? Any questions? Yeah, I guess there might be. Hi.
I think question 34.
I'm sorry?
Question 34. I think.
Question 34. Let me see if I can do this without exposing any answers here.
Just don't understand.
Okay, let me take a look at it. Now, I'm going to be out of town next week, so I'm going to have limited internet access. So it's better if you have questions on the exam, if you're working on it, if you get me the questions by, say, Saturday morning, so I can respond to them pretty quickly. I'll still be able to get to stuff within 24 to 48 hours, but I like to be able to respond a little bit faster than that. Okay, and we won't be here next week. I'll probably pre-record. If you send me questions, I'll pre-record the answers and I'll post them on Blackboard. But we'll be back the following week. There's nothing the following week. Let me think about this. Let's see, it's December. Today's the 2nd or the 1st? First. The 7th, we have the 8th is next week. That would be the 15th, right? That's the last day. Okay, so, but I'll still be here, but, I'll put up some sort of exam. When I'm back that week, I've given you a choice of a very simple project. Maybe I'll even post some sort of very simple example of something that someone did before. They did it in the form of something called a poster, but it's really basically the same thing. But I gave some instructions and some basics on it. If you upload it early, or if you get it on, up early, I'll, kind of review it and let you know if you're on the right track. You have the choice of doing that or of doing a third exam. The third exam is basically going to consist of a couple of short answers and two problems. One problem on analysis of variance and one problem on linear regression, which are the two topics that we have left this semester. Okay, so next week is going to be this week we're doing analysis of variance, next week is going to be linear regression. So then we have that week for you to get that material in by, I'll probably put the end date, I think I put the end date for the exam and for the project, I made the end date earlier, a week earlier, right? So that, if you want to do that, if you don't get it in by that time, you can just default to the exam. And it'll be the same deal. I'm going to give you a week to do it. Unlike the first exam, I'll give you the opportunity to not have to do it all in 1 3-hour sitting, right? So that you can go away, maybe play around with it a little bit and then come back to it. But it'll still be the same deal. Once you hit submit, like you're committed. Okay? If you have a problem, you can always email me with it. Boy, semester's over almost, right? Yes.
Basically, yeah. No, so the analysis of variance along with what's the last one?
Correlation and regression.
Okay. Those two will not be covered if we choose to file the project.
Well, you can, if you want, use those techniques in the project. Okay, so why would you use those techniques in the project, right? The deal here is that really what we have here is we've learned, well, at the beginning of it, we learned some basics, some stuff about probability and some, what kind of variables we might be working with. Since then, we've really been getting, each week, kind of like getting a new tool, like confidence interval, t-tests, analysis of variance, chi-square, odds ratio. Each one of these is a new tool. So just like if you have a nail, you're going to use a hammer. If you have a screw, you're going to use a screwdriver. Each one of those tests is used for different applications. So for instance, if you're evaluating the means of two numerical variables, you want to know compared to blood pressure of Americans to the blood pressure of Frenchmen. Those are numerical variables, right? You're going to calculate means and see how close they are, and variability. You'd use a t-test. If you had a situation where you wanted to compare whether people that are exposed to asbestos are more likely to get cancer than people who are not exposed to asbestos, then you'd check records on people and say, oh, this person was exposed. Yes, this person developed lung cancer. No, he did, yes, right? One or two in each direction. That's a categorical variable, like a yes or a no for the variable exposure. That would be chi-square, right? Or odds ratio. If it's a 2x2 table, you can do odds ratio. So that's the tool you use there. So now the last tool we have is analysis of variance. Analysis of variance is very much like the t-test, except that it gives you the opportunity to evaluate three or more means at the same time. We go over that quickly tonight, right? 3 or more means at the same time. So if you wanted to compare the average BMI of 7 ethnic groups at the same time, right? If you had the actual BMI, the number, for the people that you sampled within each of those populations, you could use analysis of variance to do all 7 at once, compare all 7 at once to see if any of them are different, instead of having to do a t-test with this one, and a t-test with the next two, and a t-test with the next two, and over and over and over again, right? And there's a lot of reason why you would not want to do that. Linear regression and correlation are what you would use if you want to compare two numerical variables. I'll give you an example. Anybody know the pizza principle in New York? Ever heard of that? Right? The pizza principle is that over the last 30 years or 40 years, the price of a slice of pizza has been the same as a subway fare, right? So I mean, that's kind of like a New York thing, So what does that tell you? Well, when the price is this, and they're going up together. The price is going up together. That's what you would call a correlation. You have correlations with numerical variables. That's a spurious correlation. In other words, the price of the subway is not causing the price of pizza to go up. It's probably just related to the cost of living, right? And how expenses are going up in general anyway. But there is a correlation. As one goes up, the other goes up. Another spurious correlation might be the number of firemen that show up to a fire and the amount of damage that's caused in that fire, right? Well, obviously, if it's a big fire, there's more firemen, right? And there's more damage, but it's not actually the firemen causing that. So correlation is an association between two numerical variables, right? Doesn't necessarily mean one causes the other, but that they're associated somehow. When we look at regression, we're looking at a situation where we believe that one causes the other, right? So for instance, maybe we might be looking at the number of sugary drinks that people drink per day, the amount of grams of sugar they consume per day, and their blood sugar, right? So we would say, gee, the amount of sugar that they're consuming is an independent variable, and their blood sugar is a dependent variable that depends on how much sugar that they're consuming. So as you eat more sugar, your blood sugar may be higher, right? So that's an association, a correlation, which in a case where one is actually having some impact and has some cause on the other. So one is an independent variable causing an effect on the dependent variable. We're going to be talking about that next week in videos, and unfortunately not in person, because we're an online class. But we're going to be talking about it the following week. Maybe we'll get to it and play around with it a little bit too. But we'll be talking about it going forward. So if you're evaluating, if you're going to use a database that's a numerical database, and you're comparing numerical variable 1 to numerical variable 2, you would use correlation and regression. When we really start to get into that next week, this will make sense to you. It's really simpler than it sounds. Okay, so it's really the last two topics are going to be analysis of variance and correlation. If you have a project that has multiple means and you want to compare them, you might use. We're learning analysis of variance now. You could apply it to your specific application.
So will there be homework connected to this?
Yeah, I'm going to put up I'm going to put up a simple analysis of variance problem or two and a simple correlation problem or two, just so you get something to practice with.
And I think you mentioned that with analysis of variance, it has to be done in MSP.
I'm sorry. Has to be done. What I was saying is that you probably have seen the video. The calculation of analysis of variance is a little complicated, right? So chances are you probably want to use SPSS instead of going. There is a video on there that shows you step by step, but I did it intentionally with a very small data set. In other words, three variables. Three groups, right? With only five values in each group. Now try and imagine you had 7 groups, each with 200 variables in it. Right? It'd be tough to do in Excel. Right? Just physically be tough to do even. Right? So you probably would want to use SPSS. Worst case, maybe I'll give you an alternative that if you really have trouble, I know a lot of people are still having problems getting SPSS running and with the virtual desktop and so on and so forth. So I may give you like an alternate homework or problem that you can choose to do instead that just gives you the tables, the output. So if you had gone through the motion of doing it, this is what you would have gotten, and then ask you to interpret it, ask you, what's this number mean? Would you reject the null hypothesis? That kind of stuff. Okay, so I'll try and figure some way out that like if you're really stuck and SPSS is just not working for you, that you're not trapped and not able to do it. Okay, same deal with the exam too. Although I would really like you guys to at some point, even if you have to come to school or something like that, use the machines here, to at least, have a little bit of practice doing it. Because even though I can kind of present it to you that way, it's like riding a bicycle. We could sit here and talk about how to ride a bicycle all day, but you won't learn how to ride a bicycle unless you get on the bike, right? So anyway, yeah, so we can do that. So it's really all about what's the right tool to use, right? So if you're planning on doing a project, if you upload it early, it gives me an opportunity to like glance at it and say, looks like you're on the right track, or tell you, I think you got a problem here, but you got to go back and take a look at it. Okay, problem number 30. We started talking about problem number 34. So let me go into the exam. Am I in the right spot here? Nope, I'm in the wrong class. Of course, all the guys that have already submitted, we just talked about that, submitting early and stuff like that on the homework, on the exam. Everybody that's submitting early on the exam now is probably saying, oh, no, now he's going to go over. He's going to help these guys. Don't worry, I won't give them too much information.
You have to do Monday night.
Yeah, it's due by Monday night, yes.
What's the date for the project?
It's a week before. December 12th. So if you want to do a project instead of the exam, you're welcome to do that. You got to submit it by December 12th. Reason why it's a week earlier is because I got to grade it, right? We got 60 students, and I don't know whether 3 people are going to choose to do a project or 60 people are going to choose to, so I have to be prepared for it. So if you don't want to do a project, you're willing to, or you start to look at it and you say to yourself, you know, it's not moving along. You can always just not submit anything, and that'll be I'll assume that you are going to take the exam instead. So you don't have to do anything actively to actually choose to do it, except upload. If you do it, just go ahead and upload it.
And question, you gave us a data set, right?
I gave you 2 data sets. I gave you one, which is a reduced data set, which is only material on the flu in New York City. In other words, you know, like whether a person got a flu shot or not, whether or not they're insured. One variable is, are they insured? One variable, are they married? One variable is, did they get a flu shot? Yes or no? Another variable might be there might be a numeric. I think there might be a numerical variable in there somewhere, possibly. You know, so you can play around. You can choose any 2 variables you want, or 3 variables, or whatever, and try and analyze them and put together just kind of a little abstract on what your intention is to show us, to give us some descriptive statistics. Like, in other words, since if you're going to talk about is marital status associated with whether someone would get a flu shot, you might say, well, what percentage of what proportion of the population is married? What proportion of the population got a flu shot? What proportion is insured? You might make tables or charts that will describe the population overall. And then you might go ahead and do an analysis that compares the rate that people got a flu shot if they're insured versus not insured, or if they're if they're non-American, if they're not born in the United States, if there's a difference in the rate, right? So you might use chi-square or odds ratio if it's 2 categorical variables. So, and then you might come to a conclusion. If you're really sharp, you might actually do a little bit of research and come up with an article and reference it. You know that, oh, this is what's this is what's available from this research on whether or not marital status affects getting a flu shot. I'm making that one up, so I don't know particularly that would be a good one. I don't think this will show any answers here. Good. So problem number 34. Okay, what are your conclusions with chi-square? Last 5 questions on the exam.
No,
That's not it?
No, that's the
I'm sorry. Which one? 33. 33. What is your calculated value for Pearson's chi-square for this association without the continuity correction? Remember the calculation that we did where you took each box and you took the observed values minus the expected values, squared it, and then divided by the expected values. And then you did that 4 times. For a 2x2 box, you did it 4 times for each box. And then you added that all together, right? That's your Pearson's chi-square. That's the number that's your Pearson's chi-square. So if it comes out, and the continuity correction, what that means is that, did you guys notice that if you do a table of observed values, that means you actually counted people. And so there's 34 people that got the disease that weren't exposed, and 107 that got the disease that were exposed, and there's actual people in those boxes. It's always a whole number, right? But in the true population, if you have 100 people, it might be 34.5% of the people. But you can't get 34.5 in the observed values. So in order to account for that like there's no continuity there, it just jumps from one number to the other, you take the observed values minus the expected values minus 1/2. Do that and then square it and divide by the expected values. So what does that do? That makes the top part of the equation smaller, a little bit smaller, right? Bottom part stays the same, top smaller, so that number becomes a little bit smaller, right? So when you do it for the 4 boxes, your chi-square with the continuity correction actually becomes a smaller number. So it's more conservative. In other words, it's harder for you to reject the null hypothesis because it's going to be a smaller number. For our purposes, I'm saying, forget about the continuity correction. Just do observed minus expected over squared over expected. Yes?
And if we did it in SPSS,
You should get exactly the same answer in SPSS. right? So in other words, if you do, did I do something there? Yeah, I saw some motion back there. If you do the same calculation if you go into the videos that I put up, I do a calculation that last week. I do a calculation. I run through a calculation on chi-square, doing it with Excel, and then I repeat it with the same data using SPSS, right? And you should get the same answer in Excel for Pearson's chi-square, or we might just call it chi-square, Pearson's chi-square, when you do the Excel calculation, when you do the SPSS calculation. One of the advantages, when you do the Excel calculation, you now know that the chi-square is equal to 4.2, right? So now you have to go to the chi-square table to see what the critical value of chi-square, how big it has to be for you to reject the null hypothesis. Remember, the chi-square value is bigger. The bigger the differences are between the observed values and the expected values, the bigger that chi-square calculation comes out to be. So if the chi-square calculation comes out to be 7, and then you go to your table, and your table tells you at the certainty level of 5%, right? In other words, 95% certainty and a 5% chance of being wrong. If for a 2x2 table, which is 1 degree of freedom, if it tells you that the critical value of chi-square is 3.84, and you got a value of 7, you know you can reject the null hypothesis. Of course, your p-value, your probability of being wrong, is going to be less than 5% if that value is exceeded. When you do it on SPSS, it actually tells you the probability. So instead of going to a table and saying you exceeded, telling you the critical value, it says the significance of the test is 0.02, 2%. So you know there's only 2% chance of being wrong if you reject the null hypothesis. So you actually get a p-value in SPSS rather than having to compare the critical value. Okay, maybe I can, when you go back over, you probably look at that video and you'll see where we look up that stuff on the tables.
So if we do this in SPSS, it would just shoot out the problem.
Yeah, it would give you the number. It would be in the table, right? I probably have one. So we can open it quickly. We'll take a look at what the table looks like. Was there another question up here? But some other part? Nope, this is the chi-square part is what people were interested in.
My only question was about when we're pulling standard deviations. We're choosing between the two.
Right.
You're assuming they're equal or unequal. Do we automatically?
As a general rule,
Yeah.
for our purposes, if you're not going to use SPSS, if you're doing it with Excel or with a calculator, if the two standard deviations are not double, one is not double the other, we assume equal variances. Okay, but if it's more than double, one is more than double the other, then we say to ourselves, maybe we should consider unequal variances. It's usually not going to make that big a difference in the calculation. When you use SPSS, it's a little bit clearer because SPSS actually does a test to test whether the variances are equal or not. Okay, and I'll show you that too. I think most of the stuff I gave you both sets of data, right? So you could even use SPSS to check your answer if you did it mathematically. Let's see, recently used data. I don't want to use that one. Yeah, what the hell? I'll change some numbers. Okay, I'm going to change some numbers here. Well, actually, that's only 2 variables. No. Open. I only see 2 files here. Open. Data. And it doesn't give me a search box. Boy, for a program that costs a fortune, it really doesn't. It's really primitive, in the interface. Let's say V. Let's see what this is. Okay, here's 3 groups, Group A, Group B. I think this is the one that's in the video, right? So if I look at this, I have 3 groups. Each one of them has a numerical value associated with there's 5 people in this, 5 samples in that were from group A, 5 samples that were from group B, 5 samples that were group C. So if I look at the variable table, 2 variables. One of them is a nominal variable, that's the groups, and the other is a scalar or numerical variable. Go back here, and I can do an analysis of variance. If there were only 2 groups, group A and group B, I could use a t-test, right? Since there's more than 2 groups, if I do a t-test, I would have to compare group A to group B, right, first, and then compare group A to group C, and then I would have to compare group A to group C, group B to group C, and so on. So I'd be doing this calculation multiple times. Each time I have 5% chance of being wrong when I come to my conclusion. And if I do it 4 times here, then it builds up. The level of error, probability of being wrong, if I reject null hypothesis, gets bigger and bigger. So instead of that, I use a single statistical test that will test for multiple groups means to see if they're different. So analysis of variance. I'm going to go up here, analyze, compare means. Oops, I need an output table here. On my version of SPSS, it insists on having an output table open before it will show me the path. So you compare means to analysis of variance. And in analysis of variance, I tell it the dependent, the number that I'm finding the mean of, is the measurement. And the factor, I'm breaking them up into 3 groups. The factor is the 3 groups, group A, group B, group C. Okay. If we had it in Excel, it would have been 3 columns, right? In SPSS, it's 2 columns. One variable represents the group, which could be A or B or C. The other variable represents the number associated with each outcome. So I'm going to click OK. Okay, and it does an analysis for me. I'll do it again so I can. Where to go? That means my analysis variance. Okay. Okay, let me pull this up as a matter. Okay, so analysis of variance. So if you look at this, what it's done, like in the video, like in that Excel version of this that we did, it calculated the sum of squares between the groups, the sum of squares within the groups, those 2 numbers. So between the groups, there's 3 means, right? This is the sum of squares between those 3 means, There's 2 degrees of freedom, 3 means minus 1. So that's 17.2. The degrees of freedom is 2. The mean sum of squares is 8.6. That's the number that goes in the top of the fraction for analysis of variance. Within the groups, there are 15 people total, or 15 subjects total, between 5 in each group. So it's 15 subjects minus the number of groups, which is 3. So it's the degrees of freedom is 12. But the variability, the sum of squares between all of the people in those groups is 25 divided by 12. The mean sum of squares is 2.1. And the statistic for analysis of variance is 8.6 divided by 2.1. The mean sum of squares between the groups and over the mean sum of squares within the groups. The further apart the means are, the bigger the number on top is. The more variability it is, the bigger number on the bottom is, makes the analysis of variance smaller, right? So you want a big number on top, small number on the bottom. So you want the means far apart, and you want the variability tight within each group. So that comes out to 4.095. Now, without looking any further, that's the answer you would get if you did it manually. So what do I do now that I know the F score, the analysis of variance, is equal to 4.095? Now I go to my analysis of variance table and look up what the critical value has to be for F in order for us to reject the null hypothesis. So it's a 1-by-1 table. It's 2 degrees. So I'm going to go. Actually, it's 2 degrees of freedom by 12 degrees of freedom. So I'm going to go look up a ANOVA table. So I really don't have the time to actually go through the entire calculation. And the ANOVA table is a little bit more complicated because now we have 2 degrees of freedom. We have one representing the number of means, the number of groups, and we have another representing the number of samples in all those groups. So in this case, there were 3 means, right? So that's 2 degrees of freedom for the means. So the place where the degrees of freedom between the groups is between the groups is on the top row here. So we're looking for the second row, 2 degrees of freedom. The degrees of freedom within the groups is the vertical column. Usually you can tell because it's a much bigger number that you see there. So, there's probably likely to be more subjects than there are groups. So how many people did we have? We have 15 people that were sampled. Minus 3, because it's 3 groups, is 12 degrees of freedom. So 12 degrees of freedom, our critical value is 3.89. So if our F-score that we calculated using SPSS is 4, and the critical value is 3.89, we can reject our null hypothesis. Why? Because the probability of being wrong, of getting that extreme an outcome, for the ratio of between the degrees of freedom, the variability between the means over within the means, the probability of getting that extreme an outcome is less than 5% if the groups really have the same means, if they come from the same population. So since the critical value has been exceeded, you can reject the null hypothesis and know that there's less than 5% chance you're going to be wrong. In SPSS, it actually calculates the probability of being wrong, right? It's 0.44, it's 4.4%. So since that's less than 5%, we reject the null hypothesis. Now, had the F-score, the statistics, the analysis of variance statistic, had that been 3.5, what can you tell me about the significance? Would it have been bigger or smaller than 0.05? It would have been bigger, right? Because if your chi-square, if your analysis variance doesn't exceed the critical value, you know that the likelihood of being wrong is going to be more than 5%. So they really go along with one another. Okay, and the main advantage of SPSS is it actually calculates that value because it has the specific calculations and tables built into it to do that. If you use another method, you're stuck with the table, which is okay, but you don't get that exact probability of being wrong. So, okay, so that's what we did. What was there another issue on one of these problems? Chi-square is kind of similar, right? Was there something else anybody had some trouble with on there? I was a little uncertain about. Okay, all right. It's pretty straightforward, right? Most people are submitting early are doing pretty well on it. Okay, so that's encouraging for you guys that already did it. Okay, good. How are you guys doing online? Do you have some questions there? Because I will go over a bit more the analysis of variance, so you guys can see how it works. Okay, I don't see any nasty comments, so I'll move on. Okay, so how does this whole analysis of variance thing work? And it's interesting because what we're doing is we're using variability to determine whether the means of populations are different, right? So it's kind of an interesting take on this whole thing. So the way that this works is, if you can imagine, and if you saw the videos, you probably saw me demonstrate this. One was kind of we were talking about a little hokey with the cherry trees and stuff like that, but it really is pretty illustrative of what's going on here. So let's say that we have 3 populations: population A, population B, and population C. Okay, so now let's say that indeed they have different means. The mean of this one is this, the mean of this one is this, the mean of this one is this. If we take a sample from many samples from these populations, half the time for A, the sample that we get is going to be lower than the real mean. Half the time it's going to be greater than the whole mean, right? So depending on the sample size, we're going to wind up with a normal distribution for the sample results, something like that. Let's see, I do the same thing with B, right? So, and I do the same thing with C. So what's going to happen here is if I get a result from my sample for A, and my sample result is over here, right? There's a certain probability that that sample would indicate to me that It came from, I could expect that sample to come from population A, or it could have come from population B also, right? In fact, there's almost the same probability that it came from population A as it is from population B. How do I know that? The area is about the same on both of them, to the left and to the right of A and to the left of B, right? So that could have come from either one. However, let's take the same three means. And this time, the variability, the standard deviation of these three populations is narrower. The means are the same, but the standard deviations are narrower. So when we take a sample, and in fact, when we take a large sample, right, we might find a distribution like this, right? So it's a lot easier to say that population A is different than population B, is different than population B, when the means are far enough apart and when the variability is less. So there's two things. Now I could have, let's say that A, B, and C, the means had been much different. Like in other words, the mean for A would have been here, mean for B would have been here, mean for C, I didn't leave myself much room, or over here. So the same amount of variability would look like this, right? So it's pretty easy to tell this one's different, right, than the other samples, because it's very unlikely I would get from B or A sample that's anywhere near the expected values we would get for samples from group C, right? So what do we have here? It's good. Good things are that the means, the means are very different. In other words, the standard deviation of the means is very different. They're very far apart, and that the standard deviation within the groups, in other words, the standard deviations of each sample, is very small. We want this to be big, we want this to be small. And the bigger the difference between the means and the smaller the variation within the groups, the more certain that we can be that they're really different. And how do we calculate that? We calculated that by putting the variability for the means on top and the variability for within the groups on the bottom, right? How do we describe that? We describe that as the sum of squares divided by the degrees of freedom. That's the same way we calculated variance. Remember when we stood at the beginning of the semester, we took each individual value, right? In this case, each mean. We calculated the difference between each mean and the average of all three means. We then took that number and squared it, right? The squares of the differences between the value and the mean. And then we added them all together for the sum of squares, and then we divided by n minus 1 degrees of freedom. So this is really the same as finding the standard deviation. So here's the variability for the means over the variability within that. Now, the bottom is the same deal. It's the sum of squares within the groups divided by the degrees of freedom between the groups. Oh, you need to get that out?
Yes.
Okay. Should I push this up? You're going to work, which way you want to go?
In front of it.
Okay. Yeah, let me get my bag
Sorry
off of
to
there.
interrupt.
No problem. Yeah, watch out for that cable. Oh, thanks. Okay, good, thanks. Can you get by there?
Oh, yeah.
So in the video that I made, literally, I took these numbers. Let me open up the Excel version of that. I actually tell you the truth, let me not bother. I'm going to do another example of calculating the analysis of variance. And for that, I'm going to open up a data file that has a lot of data in it. Oops, that's a Word document. Let me get rid of that. And see birth. Okay, here's the data. It has lots of information. It's about I think it's a sample of 800 births in North Carolina. It has information about whether the mother smoked, how much weight she gained during pregnancy, the race of the mother, the weeks of gestation, the mother's age, the gender of the child that was born, if the mother drank, the weight of the child. So let's take a look at this. So let's see what I might be interested in looking at here. So if I'm looking at a t-test, I might be interested. Let's see if married versus not married women gained different amounts of weight during pregnancy. What kind of variable is married or not married? Nominal, right? It's a categorical variable. What kind of variable is the amount of weight gained? Numerical. Numerical variable, categorical variable. We're going to find the mean of those two groups. Mean weight gained for mothers that were married, mean of weight gained for mothers that were not married. So I'm going to use a t-test. So I go to Analyze. I'm going to build up the analysis of variance. Go to Analyze, and I'll go to Compare Means. And of course, I have to get the output window up front. So you can see me just kind of a pain in the butt. Analyze, Compare Means, Independent Samples t-tests, right? Males and females. Okay, and I'm going to put in here the weight gained during pregnancy is a test variable, what we're going to find the mean of. And the grouping variable is going to be the marital status of the mother.
Compare means and
I went to Analyze, Compare Means, and I went to Independent Samples t-test. It's not a single sample t-test because I'm not comparing one sample to a known number. And it's not paired samples because it's not like a mother's weight before and after or something like that. It's actually different women, right? Some married, some not married, two different groups. So I'm going to guess and say that this is 1 and 2. I'm hoping. Maybe it's 0 and 1. I'll start with 0 and 1. Hopefully I get that right. I should have looked at it first, but okay. So let's see if it works. Okay, no, it didn't work because I got that wrong. Analyze. Compare means, independent sample t-test, except this time let me define it, and it's 1 and 2. I don't remember which one represents which. We could have looked at that if I looked at the variable view. Okay, this time it worked. So what did it do? It did a t-test. First thing it did was it calculated the likelihood. It did a test for the equality of variances, right? It's called Levene's test. These 4 boxes here test whether the variabilities of the two groups, married versus unmarried women, is the same. The default is, just like with the null hypothesis, the default is that the variability is the same. So our default, our null hypothesis, is that there are equal variances, and we're going to use the top line. If it turns out that that's wrong and we reject that idea, then we use the bottom line. Okay, so let's see what our value was. It's not the analysis of variance, different statistic, but the significance, the p-value, is 0.001. There's less than 5% chance of being wrong if I reject the null hypothesis. What was the null hypothesis? That the variances are equal. So I don't use the top line. I use the bottom line. Had that significance been bigger than 5%, I would have stayed with the top line. So I use the bottom line. So the bottom line tells me the t-test is negative 0.063, and the probability of being wrong if I reject the null hypothesis is 95%. So clearly, there's not enough evidence for me to say that there's a difference between the weight gain for married women and unmarried women. Let me do it for something else. Analyze, compare means, independent samples t-test. Let's do it for a different variable. How about whether they smoked during pregnancy? Let me get rid of this one. Smoked during pregnancy and the weight of the child. Okay, I'm going to do the same analysis. Okay, now I got to tell it to find the groups again. Hopefully 1 and 2 is right. And no, of course, it was the other way with that one. Just my luck. It must have been 0 and 1. Okay, let's see what happens here. Okay, well, in this case, the significance for my quality of the variance is 0.344, which is bigger than 0.05, so I stay with the top line. I can't reject their being equal. So I go across the top line, the t-score for the difference between the means for the mean weight gain, the mean birth weight of a child for smoking mothers versus non-smoking mothers, the difference, the t-score is 3.5. We know that's a big difference. We know that's pretty big, right? Okay, so if I go across here, what's the probability of being wrong if I reject the null hypothesis? It's less than 1/10 of 1%, less than 0.001. So our null hypothesis was there's no difference between the two means. Let's take a look. Let's go up here. For instance, if you're doing this as a project, let's go up here, look at descriptive statistics, look at explore. Let's look at the weight of the child in ounces versus the mother's smoking status. Marital status. We didn't see a difference from marital status. That's the weight of the child in ounces, right? And where's the smoking status? Here it is, smoke during pregnancy. I'll move that in there, and it's going to calculate 95% confidence intervals and so on and so forth. I'm going to click OK and see what it comes up with. Let's see. The average birth weight of a child in ounces to mothers who did not smoke was 117 grams, and mothers who did smoke was only 109 grams, right? We have the standard deviation, the confidence intervals. We even have a box plot that compares the two of them. These are outliers over here, right? Notice there's not many outliers on the top. There are mostly outliers on the bottom. Why is that? Right? You don't get too many babies that are over like 9 or 10 pounds, right? Right? But you get a lot of premature births, right? Where you can have very underweight babies. So as it happens, but you can see that the mean is different on the two of them. Now, these are such big samples that even this difference in the medians or the spreads is enough for you to prove statistically that there's a difference among smoking versus non-smoking mothers. That means smoking does it? You never know, right? Because it could be other health choices that they're making. Maybe mothers that smoke don't go to the obstetrician as often or something like that. They don't have a good diet.
Listen, on this one, is mothers did not smoke. They had other outliers.
Yeah, because they're more premature births.
Yeah.
That's kind of odd, right?
Yeah.
However, the average weight is higher. And you know why there's more? Because if you go back in here, how many mothers do you have that smoked? You had 114 mothers that smoked, but you had 700 mothers that were non-smokers. So what you're seeing there is a lot of premature births because it's a lot more births, right? So maybe maybe it's really the same number. Who knows? But on the average, they do. So let's.
Because you can't say that there's association.
Oh, you can say that there's an association because what was our t-test again? Remember what our t-test was? See, when we did it for marital status, our t-test was very small.
Number of factors.
What's that?
That
Yeah, well, there is a difference. We can say with 95% certainty there's a difference in the mean weight of mothers who smoked versus mothers who didn't smoke. And then I had to open my mouth up and say that, oh, by the way, may not be actually the smoking that's doing it, but it may be other health choices. But that doesn't change the fact that there is a statistically proven difference.
you would say difference or not.
Yeah, I wouldn't have gone. I should have kept my mouth shut, at least for this course anyway. Right. So yeah, I mean, when we talk about correlation and regression, this idea of whether or not this causality is going to become even more important.
Can we see the curve for the two?
What's that?
Is it possible to see the distribution curve for the two?
Oh, whether they're normal or not? Sure.
Yeah, because
Analyze.
it looks like the one to the left would be skewed.
You're probably right. Okay. Let me see. Independent samples t-test. I can go in here and ask it to do options. Oh, no, I can't do it there. Oh, I got to go to explore. Compare descriptive statistics. Explore. I can go in here and ask it to do a histogram for me. There it is. Can't even ask it to maybe throw a line in there.
Yes, to do a what?
A histogram for the two variables. Let me just take this quickly. Hi, Stavros. I'm in class. Can I talk to you later? Oh, okay. I'm done at 5:30. Maybe what's the office? Okay, I'll track you down. Okay, good. Bye. Okay. So yeah, you're right. Look, it's skewed, isn't it? Right? Now, we have a very large sample here, so we can tolerate some more, variability from normality, with this test because our sample size is really so large. And we also skewed here also, but it's skewed for a reason, right? We were just talking about that. You don't get too many, if the average birth weight is 7 or 8 pounds, you don't get too many babies born. It's very rare to get a baby born bigger than 10 pounds, but it's not rare if the average is 7 pounds to get a baby that's born at 3 pounds, much different, or 2 pounds even, right? So, or a number of ounces. On the first one, when we were talking about marital status, in that one, we failed to reject the null hypothesis, right? Now, you don't say accept the null because you didn't prove the null. You just failed to have enough evidence to reject it. So we failed to reject the null hypothesis. On the second test, where the t-score was 3.5 or something like that, that one we reject the null hypothesis that there's no association between the mean weight for babies born to mothers who smoke is equal to mean weight for babies mothers who didn't smoke. We reject that and accept the alternative that there is a difference between the mean weights. Okay. So now, what about if I want to look at more than one variable? Let's see. I mean more than one value for a variable. For instance, such as for the race of the mother. I'm going to click that and click OK. Now, in this case, how many groups do we have now? Now, these other charts here were charts where you would use them to test the normality of your outcome. Okay, so let me see what happened here. I thought I did. Right, let me try it again. Analyze, descriptive statistics, explore. Yeah. Yep. I didn't put anything into the factors. Race of the mother. I put the weight of the child is still there. I'm going to put the race of the mother into the factor list. Now, there's going to be more groups there, right? There's going to be Hispanic, Black, white. So now I'm comparing more than two means, right? So I'm going to click OK. And now, my descriptive statistics, let's see. The average birth weight of the child for white mothers was 118 ounces. For Black mothers was 108. For American Indian, it was 113. For Chinese, it was 126. That's big babies, eh? Wow. For Asian Pacific Islanders, 129. And that's why now I know why you have so many Samoan guys in the NFL, right? Playing football. Right. It went under factor. Yeah. So we broke it up, and factor means break it up into groups. So we're comparing the means for 4 groups here at the same time.
Statistics.
Well, now we're about to do that. Now we want to actually test. What's our null hypothesis for analysis of variance? The mean birth weight for Chinese mothers, for Black mothers, for white mothers, for Asian Pacific Islander mothers are all equal. U1 and U2 and U3, all equal. What's the alternative hypothesis? They're not all equal. At least one is different than the others. So my analysis of variance allows me to do those all at once. It's going to go in here to compare means, go down to analysis of variance. Again, we're comparing means, but we're doing it by checking the variability, right? So it's a neat trick, isn't it? So our dependent, our number is going to be the weight of the child. Weight of the child, I'm moving in there. And the factor is going to be the race of the mother. Okay, those are the groups going to be broken up into. So I'm going to go ahead and click OK. Okay, and it's going to do that analysis for me. Okay, and here it is down there. I'll bring it up a little higher. And what does it come up with? Well, the sum of squares between the groups, there's 4 groups, right? So the degrees of freedom, I'm sorry, there were 5 groups apparently, because the degrees of freedom are 5. We know it was 6, I guess. It's been 6. Degrees of freedom, there's 6 means. So there's 5 degrees of freedom. So this divided by the 5 is the mean squares. That's the number goes on top. And this is the sum of squares for the 800 women that are there, minus 6 groups is degrees of freedom 794. So this divided by 794 comes out to this number. The F statistic is the mean sum of squares between the means divided by the mean sum of squares within the groups, right? It comes out to 5, and the significance comes out to be 0.000. What does that tell you, that 0.000? Can we reject our null hypothesis? Reject our null hypothesis, because the chances of being wrong if we reject our null hypothesis are less than 5%. Now, did this tell you which of the groups are statistically significant? It didn't. It just told you that mu1, mu2, mu2 equal mu2. That's wrong. That's all it's told you so far. So now we have to figure out which of the groups are really different. So now we need a function in here in analysis of variance that will do the actual comparison group to group, individual group to group. Those are called post-hoc tests. So now that you've determined this, now if this significance, that number were greater than 0.05, would I reject the null hypothesis? No, you'd fail to reject it. You can't say that they're different. So what do I do then? I do nothing, because I failed to prove that there's any differences between the means. But now that I have proved that there's a difference between the means, now I want to determine where the difference is. So now I go back in here and I say analyze. I go back to compare means, analysis of variance, and this time I click in here to post hoc. Post hoc means is Latin for after the fact. After we've proved that we can reject the null hypothesis, now we can ask it to tell us which of these groups, do a group-to-group comparison to tell us which of them are statistically significant. Right? Well, let's see what we have a whole bunch of choices here. Probably the most common, some of these are like Tukey, is simply a way of reducing the tolerance for error. Like if it's 6 groups instead of 5%, or tolerance for error is like less than 1%, and kind of recalculating it to 5%. They all use different strategies for telling you whether or not the different groups are statistically different. The different means are individually one to the other statistically different. So it's going to compare each group to the other group. So with 6 groups, it's going to do a lot of comparisons, right? One to A to B, A to C, A to D, B to D, E to C to F, C to, and so on and so forth. So I'm going to click Bonferroni. Bonferroni and Tukey are probably the 2 most commonly used ones. I'm going to click continue, and now
You didn't choose 30.
I'm sorry, I didn't choose. No, I'm going to choose Bonferroni first. Okay, just so it's a little bit simpler when the table comes out. The table's going to be pretty complicated to start out with. Okay, so now let's see what I got. Okay, post-hoc test not performed weighted child because at least one group has fewer than 2 cases. Uh-oh. Who is the group that has fewer than 2 cases? Race of the mother. Data. Sort. Where's sort? Sort cases. Sort cases. Okay, sort the race of the mother. I'm going to sort this by the race of the mother to find out which one of these cases has the fewest number. There's only 2. It's too small a sample. Other island Pacific. Yeah, I see Chinese and Filipino. So I'm going to get rid of those 2. Okay, now I'm going to try it again. Oh, I got it on the output page. Like I said, there's a bug in here. I don't know why it does that. Compare means, analysis of variance. Okay, so I'm going to try this again. Cross my fingers. Oh, and it worked this time. So we're down to 4 groups because I eliminated 2 of them. But let's look at the comparison. What it did was it compared whites to blacks for the mean. The mean difference in ounces was 9.4. It compared whites to American Indians, white to other Asian and other Pacific Islanders, blacks to white. And look, it repeated the same analysis because it goes through every permutation. So if I go over here to the significance, this is the probability that I would be wrong if I said that the means of those 2 groups were different. So what am I looking for here? I'm looking for numbers that are less than 0.05. So this one is 1.0. This one is 0.516. So basically, it's saying that you can't reject the null hypothesis that whites and American Indians are different birth weights, whites and Pacific Islanders, but you can reject the null hypothesis that white births and black births are the same average weight. That significance is 0. You can also say that blacks and Asian Pacific Islanders is different as well, because the probability of being wrong if you reject that particular null hypothesis, mu for blacks versus mu for Asian Pacific Islanders, is it's less than 0.05, so you can reject that null hypothesis. So, and if you notice that it just winds up repeating these several times, but the results will always be the same. Asian Pacific Islander, American Indians is not significant. Asian Pacific Islander black is significant, but you already knew that because you'd found it out up here as well. So it goes through all the permutations. If you look at the significant, it tells you which one you can say that there's less than 5% chance of being wrong if you say that the means are different. So that's the tool. This is a tool. The analysis of variance is a tool that gives you a way to compare the means of many groups at the same time. Right? It could be baseball teams. If you wanted to know the average, how many baseball teams are there now? 32 or something like that. If you wanted to know the average team batting average for 32 teams and see if they're statistically different, right? You could do analysis of variance with 32 groups, right? And then do a post-hoc. If it came out that there was that ANOVA told you the probability is less than 0.05, that the means are all the same, then you could do a post-hoc test to see which teams are statistically different from the other teams. Right? So anytime you have more than 2 means that you want to compare, like in this case, means based on ethnicity, you use analysis of variance instead of doing the t-test. You could do the t-test and just do it over and over again with each different group. Group A versus Group B. Blacks versus whites, black versus Asian Pacific Islanders, black versus American Indians, white versus American Indians. You could do it that way if you wanted, but each time you do it, 5% chance of being wrong. So cumulatively, the error builds up. This is a better way to do it. So that's what you use this for. Now, interestingly enough, if I had only 2 groups and I calculated my analysis of variance and my significance, my result would be the same thing as doing a t-test, which is kind of interesting, right? Because it seems like we're doing something very different than the t-test. We're really doing something that's the same as the t-test, but we're extending it to more groups. Right? You can kind of see that when you actually just do the t-test, because when you do the t-test, you really are kind of comparing variabilities. Variability between 2 means versus variability within the 2 groups. Right? So in a sense, the t-test, analysis variance, kind of vary. They're in the same family of tests. Right? And like I said, you can prove it to yourself by taking something that only has 2 groups, and doing analysis, doing a t-test and doing an analysis of variance on it with only 2 groups.
When you did a post-hoc, you checked off Bonferroni.
Yeah, let me try Tukey. Let's see if Tukey gives us a different answer. Some of these are more conservative than others. Some of them have a bet. Yeah, you could do both. Sure. Let's see. Analyze, compare means, one-way knows. Some are more conservative than others. Some are better for certain kinds of data. Okay, so let's see. Tukey. So let's see, the significance we got for white versus Asian Pacific Islander is 0.315. How about if we use Bonferroni? White versus Asian Pacific Islander. Oh, look at that. That's interesting. Right? Bonferroni is 0.516. Tukey, right, is 0.315. Hang on a second. No, they actually, Tukey gave us a lower probability of being wrong, but they're both more than 0.05. So they wouldn't affect the outcome. Is there any that are really close? 0.11. Black versus Asian Pacific Islander. How about here? Black versus 0.1. A little bit of difference, tiny bit of difference, but not much. It still rejects the null hypothesis in both cases. So we got similar results anyway from the 2 of them. Like I said, if you are going on to the next class in statistics, advanced classes in statistics, you'll probably learn more about why you would use what the basis of these tests is, why they work, and why you would use one over another in a particular application. Okay? So that's analysis of variance. And you want to know something? I'm going to put this in that North Carolina birth set. I'm going to like eliminate those ones that don't have much frequency on race, and maybe clean it up a little bit more. And I'll put this up, and if you want to use this for your project, you can use this data set also. This is like from the 90s, I think. It's old. It's old. I could probably maybe on their Department of Health website for North Carolina, might be able to find some fresher data. But I mean, rather than this, actually a subset of the data. There's really, I think, it had all the births in it. The original data set might be 50,000 births or something like that. So we cut it down to 800 because the student version of SPSS that we used to use, like about 6 or 7 years ago, would only allow you to put in 800 cases. Well, you had a limit of 50 variables and 800 cases, right? That's why we cut it down to 800. Right? So that's just for our convenience. But I'll say, I'll put this up so you have an extra data set that you might want to play around with. You can look at what the variables are, see if you want to examine some association, whether mother's drinking affected the birth weight of the babies, whether the likelihood, there's also there's variable in here, premature, yes or no. So you could compare something that's a categorical variable, like the sex of the baby, to male, female, to whether it's premature or not, to see if there's some association there. Since it's two categorical variables, you would use chi-square or odds ratio. So the real deal on choosing the project over choosing the exam is that the project, I want to see you like actually use one of these tests and demonstrate that you know how to apply stuff like that, right? Yes.
Okay, so just one more time so that I understand. Before the variances and analysis of variances, we just went through the whole thing.
Yep.
But for those who cannot access SPS,
I would not try it with Excel because it's going to be pretty different. With a big data set,
right,
it's going to be pretty difficult to do. Yeah, if you want to see it done, there's a video on there where they actually do an example of analysis of variance for 3 groups, Group A, Group B, Group C, and five cases in each group. Right, so you can see it's how the math actually works.
So if we don't have SPS, we can't do the SPS. Are you going to give us the data?
On the exam, I will give you an option of either, maybe what I'll do is I'll do like 2 possible outcomes. Like you do one problem where you just do the analysis yourself and produce the table and so on and so forth. And another one where you have to do a little bit, I'll give you the tables, but you have to do a little extra. So to make sure nobody's shut out because they have the problems. Because I know that instead of like encouraging people to buy SPSS, they put up this virtual desktop thing. So, and I haven't had much success with it. It runs slow and it's buggy for me. So I imagine you guys have the same experience. Although you should try it. They've played with it a bit, so it might be better now than it was before. Should I put the instructions up again on how to get to it? Yeah, I'll put them up again. Maybe you guys can experiment with it and be a little bit better.
For the earlier example,
Sure. I'm sorry?
For the earlier example, the confidence range doesn't do anything to us, right?
Well, let's see.
Unless it's not like in chi-square where you.
Well, let's see.
Check
That's the difference in weights, right? That's the mean difference in weights. So let's see. If we had a significance of 0.000, the 95% confidence for the real difference in white weights versus black weights is 4 to 14. What number do you not see in there?
0.
0, right. So since 0, so the null hypothesis, mean weight for black babies versus mean weight for white babies, null hypothesis is the 2 means are equal. That's the same thing as saying the difference is 0, right? So since you don't see 0 in that confidence interval, That's another means of proving that the null hypothesis is, you can reject the null hypothesis. Yes,
Check the off going forward.
Yeah.
It didn't come up. Like,
click. Oh, because you didn't delete those two ethnicities,
oh,
right? Remember, it comes up with, it should come up, scroll up. It should come up with a warning button. No, the other way. The other up, whatever that. Oh, wait a second. Yeah, it didn't come up, did it?
no.
It should come up with a warning. Oh, was that a warning there? Scroll again. Keep going.
Yeah, warning.
Yeah. Does it say that there's the group?
For weight of child, because at least one group has fewer than two.
Right. So when I went in there, I sorted I sorted it by race, and I eliminated. There were only 2 Chinese babies, and only
One Filipino.
1 Filipino. So I got rid of those 2 groups, right? Because it wouldn't do it unless, I think, probably 5. Probably if you have less than 5 in a group, probably won't do it.